So in this session, we'll focus on the damage analysis on Lifelines. We are looking at the electric power facility damage analysis and the same damage analysis. So when I start, I'm going to explain the water facilities damage for a few minutes for the first part, and I'll take a break for a couple of minutes to see if you have any questions, because some of the concepts in the electric power facilities will be repeated in the roadways. So if you have any questions, it might be a good idea to ask them. So for the electric power facilities and the roadway damage analysis, we'll use a tsunami that is based off seaside testbed. And for the water facilities and buried pipelines, we will use an earthquake that is around the Memphis area in Shelby County. Okay. So the first step of this notebook is to import the modules that we need. From these, we have seen these in the earlier sessions. It imports in core client, that is the hazard facility service, and the data set and the mapping set objects, which will be used for calculating the damage and loading the data sets. And we import pandas. On this, okay. And the next part is we will also try to visualize the outputs and also the input data sets. For that, we'll use some modules of Pinecore Viz. We'll import the GeoUtil that we saw in the previous notebooks. We use plot util from Pinecore Viz, and this globals is just to see which version of Pinecore Viz is installed. Okay, so here we are initializing the in-core. This should be my username or password. If I have already entered it previously, it will just reuse it. I think it will work. This session is usually valid for 8 or 10 hours. So, okay, so. Okay, so I have successfully logged in. The version detected is Pinecore 1.20, and I'm printing the Pinecore Viz version that's installed, which is 1.4.1. So the tsunami that we're using here is a data set based tsunami for a 500 years recurrence interval. So this is, we're initializing a hazard type as tsunami, a hazard ID. This is the ID of the hazard. And the demand type we are using is Hmax, which I believe is inundation depth. And we are initializing the tsunami JSON by reading, by getting it get tsunami hazard match part of the hazard service. We pass the hazard service object that was initialized here, and we pass the hazard ID from here. So I'll run this. Okay, and in this step, we are trying to see what's a raster that is behind this tsunami. So if we are using a GeoViz method to plot raster dataset, and we pass the dataset ID from here. To demonstrate this, I can also show like how to what is exactly part of this hazard. So on the in-core site, we have all these viewers. So if you go to the hazard viewer, you can select tsunami, and you can type the ID from the notebook here. It will show what the it will show the tsunami. So this will show that this has 3 different data sets. So each of them is linked with, if you download the metadata and open it, you'll see that each of them is linked with one particular demand type. One should be Mmax, which is the momentum flow. Other should be Vmax, which is the velocity, and the other should be the Hmax. So if you preview one of them, it will show like where the raster is based off. So that's what we are seeing. I'm just getting one of those three rasters that is specific to H max, and I'm plotting it here. Okay. Okay. In this part, we will see how the electric power facility damage will work. So this electric power facility is based off a particular hazard. And in this section, as we discussed before, it's a probabilistic tsunami with 500 years recoverable. This is the process for computing the structural damage. It's the same as, it's not exactly the same, but it's similar to the building damage analysis that Chen previewed in the previous session. We use a fragility mapping, that is a set of fragilities that apply to each of these in each of the electric power poles and substations, and we use that to we use that to find out what's the hazard intensity at each location, and we'll use the hazard values for H max, and we'll determine the probability of exceeding each limit state, and use that limit state probabilities to calculate the probability of damage. So in the end, we will see what's the output of this analysis, and how they are categorized into different damage states, which we call as DS0, DS1, up until DS5 here. And also for earthquakes, we can also use soil information to calculate the liquefaction and apply the liquefaction probabilities and adjust the actual damage probabilities with the liquefaction probability, and see what the and how it impacts the overall damage states. We'll see that in the following analysis with water facilities and water pipelines. So for now, at this point, we'll see how the electric power facility with tsunami is. We'll initialize the EPF ID with a particular ID from our database. So similarly, this is a dataset ID. So we can go to our in-core viewer, go to the datasets, data viewer. In this data viewer, you can see all the different data types that we have. And we can search it directly by the ID. This was created research from OSU, who are working on the seaside testbed. You can download the dataset, you can preview it. This dataset only contains the poles and substations. If I preview it, it'll show it here. We'll also see how we can preview this by using Pinecore Viz visualization methods. So this is the dataset, and we put it into a dataset object using this method, and then we are converting it into a data frame, so we can visualize it and see what's the content of this dataset. So if I run this, it will show that it'll show the attributes of this dataset. It has all these columns. It has GUID. I'm only showing the first 5 rows. So it shows what's a pole type, what's the, I think this is facility type. So it says ESSL2, EDCC, and all this. So what this means is EDC2 means distribution circuits. This L is low voltage. So if I group it by the utility type, it shows that this dataset has 332 poles and 1 substation. This is for the seaside testbed. And if I plot it, it'll show everything as a blue dot. I could use the other plotting methods similar to what Chen showed in the building damage to show a different legend for a different color for each of the structure type based on if it's a pole or if it's a substation. Okay, now this is the part where we run the damage analysis. So we import the Pinecore EPF damage module, utilize the EPF damage. Okay, and here we are loading the remote input data set called EPF ID, which is just a string form of this ID that we saw in cell 5. And then the hazard type is going to be tsunami. So this supports multiple hazard types. I think it supports 4 hazards. I'll show you the documentation a little later. So the hazard type is going to be tsunami, and the hazard ID is going to be the same ID that's hexadecimal ID here. And this is where we initialize a fragility service, and we have a mapping ID. The mapping ID is going to be, I'll show what the mapping ID is. So if I select this mapping ID and go back here, you can select a DFR3 viewer, and you can search for this mapping ID, and you'll see that there's a mapping ID here that's created for tsunami electric facilities. So if you select this, what this is saying is, if the utility type, if the facility type is ESSL2, use this particular fragility. And if it is EDC2, which is distribution circuit, which is a pole here, use this fragility ID. And this is specific to inundation depth. So this can have like multiple rows here, one for inundation depth, one for velocity, one for momentum flux, and all the different demand types we support. So this is only specific to inundation depth. So I can show what this means. These are mappings. So, and then we have a lot of DFR3 curves. We have over 10,000. We have over 10,000 different fragility curves in our database that support multiple hazards, multiple inventories. So if I go to the electric power facility, I can see all these different curves. I'll paste the one that I previously chose from the mapping. This is the mapping that's specific to the, I think, EDC2, which is distribution circuits. Okay. So this is what this particular curve is stored as. So we store it as a SciPy distribution curve, where it takes input as one of the damage values, and it calculates it based on this expression. So if it's a slide for limit state 0, this is the expression. For limit state 1, it's this, and so forth. And the input parameter for each of this expression is Hmax. And for other hazards where there are multiple demand types, we can provide multiple parameters and use multiple demand types in the same equation too. Okay, going back to the notebook. So this is a mapping ID, and here we are loading the mapping ID into a mapping set object. We are setting it as an input data set. And we are setting the parameter as non-retrofit inundation fragility ID code. This can be anything arbitrary that the creator of these fragilities used. So if I go back to the fragility viewer, it basically means this is a key that the user has used. If this is something like just inundation depth here, even on the notebook, it has to say inundation depth. And what this is saying is use 4 CPUs for parallelization and faster processing of the analysis. And the result name is Seaside Tsunami EPF Damage. Based on this name, we can create the output data set, and it also uses this name to create the output CSV files. So now if I execute this cell, the analysis should run. Okay. Now the analysis is run. Okay, if I refresh this, I see that it created 2 files. This is similar to the building damage analysis, where one of the files will show the damage state and limit states, and the other one will show the hazard values, the fragility used. If there is time at the end of the session, I can go into detail of what these the content of these files. Okay, now if we see the output, this is nothing but this is trying to load the result into a data frame. Okay. So this is the output of this file. This is actually we are also merging the utility type and geometry from the input data set. So this is the output for this GUID. The limit states is 0. It's because some of the power facilities are not exposed to hazard. So there are a few that are not exposed and some are exposed which have yes, and the ones with the yes have some non-zero limit states and damage states. Okay. So we can see how we can also visualize the damage states on a map. So here I am trying to see how this data set, loading this data set on a map along with the data set result. And we are trying to see the probability of each of this building falling in damage state 2, which is moderate damage state. This is a bit too small. Okay, I don't know why it's doing this. Okay, anyway, what this means is there is a legend here. So the lighter it goes, it means there's more damage. So the ones actually around here have a high probability of being in damage state 2. And the ones over here have less probability of being in damage state 2. We can change this to be something else, damage state 4. There are actually very few that are in damage state 4. Okay. Similarly, you can change it for any damage state and see how it looks. Okay, these are the same output visualizations from the building damage analysis, where we are trying to group them by the facility type. So for EDC2, the mean value of damage state 0 is this, damage state 4 is this, and the total count is 322 units, and there's only one substation. Similarly, this one is a stacked graph of each damage state grouped by the facility type. So for ESL2, everything there's no damage, everything falls under no damage. And for the poles, they are 60 they are most of them fall under damage state 0, and this is the distribution for the rest. Okay. And this is the graph for this is trying to group a particular damage state into different bins. So there are so many that fall between 0.0 to 0.1 bin. Over here, like more than 200 of the units fall under the first bin, and the rest of them are distributed this way. Okay. So maybe I can briefly show these files too. So if I see the file, the damage outputs, it will be the GUID, which is a unique identifier for each of these inventory items. And these are the limit state probabilities. These are all zeros, probably because it's not exposed to the hazard. Like these units are not exposed to hazard. And so that everything has DS0 is always 1 in those cases. And the ones that have yes have these limit states and these different damage states. And this is a JSON file. This is a previewer of this JSON file in Jupyter Notebook, so it shows like a tree in a tree mode. So for HMAX, these are the demand units, and the hazard value is, I think this is not exposed, so that's why the hazard value is none. But if you see something else, there should be hazard values. Okay. I'll stop for a couple of minutes if you have any questions. Check chat. Okay, if we don't have questions, I could move ahead to the roadway damage. Okay. So the next part of this is the roadway damage analysis. This analysis computes the roadway damage based on earthquake. Uh, or maybe before this, I'll show like the documentation we have for EPF and the roadway damage analysis. So if you go to our in-core site, you can see the user guides. In the user guide, you can click on the in-core manual. You can go to PyInCore and analysis. You'll see all the different analysis that we support. So the one we discussed right now is electric power facility damage. This shows like what all hazards are supported and what are the different input types and what are the input data sets that have to be provided. And what are the required fields. The one that show with the star are the required fields, and the others are optional that can be assigned a few default values internally. And what are the required output fields. So the one we are going to discuss next is the roadway damage. So you can go here and see what are the supported hazards. So the supported hazards are only earthquake and tsunami for this. And these are the specific input types. Okay, I'll start with the roadway damage analysis. So we are using the same tsunami that we initialized in the previous step, which is for seaside 500-year recurrence interval tsunami. So I'm initializing a roadway dataset string here, which is a unique identifier for this. Oops, wrong comment. The road data, we are loading it into a dataset object, and similarly loading the data set into a data frame so we can see what's input here, and trying to plot the map, trying to plot the roads on a map using the PineCore Viz method called plot map. Okay, so in this data set there are like there are a lot of roads. This is the division of map by the highway field of the dataset. They are categorized as added, living street, primary, residential, service road. Yeah, all these different roads. So these are the different attributes in this dataset: from node to node, length of the road. Yeah, the geometry to show the latitude, longitude, the location of the road. So if we are visualizing using the plot map method of PineCore Viz, this is how it looks. These are the different roadways. Okay. So we'll use this input data set to run the roadway damage analysis. So we initialize the PineCore analysis roadway damage. We initialize the roadway damage object with the roadway damage object. And we load a remote input data set called roads. So you can get what these inputs should be from the roadway damage class. So if you see, this says that one of the key name for the input data set should be roads. So I know that when we create this analysis, there's a required parameter called roads, and initialized it with the roadway dataset ID that we are using in this cell. So I initialized it to roadways, and we use hazard type as tsunami from the previous step. Hazard ID is the same tsunami ID, and similarly we use fragility service. Mapping ID is this. I can check what this mapping ID is. This is a DFR3 viewer. Okay, so it looks like all the different roads are mapped to a single fragility. So that's why we don't have any rules defined here, because we only have one fragility that's being used for all the roads. So if I search with this, it will show that this is the fragility we are using. is H max, and this is the expression that's being used to calculate each of the limit states. Limit state 0, 1, 2, 3. Okay, so we initialize the mapping ID, and we try to initialize it to a particular mapping set object, and then load it into the DFR3 mapping set, which can be found. These keys can be found from the road damage analysis that I showed. And the fragility key is going to be non-retrofit inundation fragility ID code, which was used by the author of this, not author, like the person who created this fragility in our system used this key. And we are setting the number of CPUs as 4. This can be anything. This can even be 1. The road damage, this is the output. The result name should be this. And then we run the analysis. So if I run it, it should create 2 more files. This is also a smaller data set, so it ran pretty quick. It created these 2 files. And we are loading this into the roadway damage result object, and then loading it again into a data frame to see how it looks like. Okay, it's similar to the other output. For this GUID, these are the limit states, these are the damage states, and if each of these units are exposed to hazard or not is represented on this field. So if we are trying to visualize it on a map, we use the same method called plot join map. Okay, and we are trying to visualize it for a single damage state, which is damage state 3, which represents extensive damage. So similarly, the one closer to the coast have like more probability to be in extensive damage, and the ones here are less affected, I guess. They have less probability to be in damage state 3. I can also quickly show like what these methods mean and where the manuals are. I think this was also covered in one of the previous sections, but if you go to the Pinecore Viz documentation, you can go to Pinecore Viz, and in this we are using this method GeoViz plot join map. So you can see that in Geo, it's part of the GeoUtil package, and you can see plot PDF map. So this is the documentation relevant to this. It shows like what is the parameters and what are their default values, and what map provider we are using on the background. Like we can use different providers to see different layouts. Okay, I'll go to the next lifeline analysis, which is based on earthquake hazard for Shelby County. So in this, we are going to focus on water facilities and buried water pipelines based off the Memphis testbed and Shelby County. So similar to how we initialize the tsunami, we are going to use a hazard type, which is earthquake. The hazard ID is this particular ID, and the demand type that will be used for calculating the damage is going to be PGA. And we'll get the earthquake JSON from here. And this is not needed unless you want to print and see how the earthquake JSON looks. You can also see more metadata of this hazard by going to the hazard viewer and searching for it. You can see this follows Atkinson and Boer 1995 model-based earthquake, and these are the metadata for this earthquake. Okay, going back to the notebook. So if we plot this earthquake, we can see how it looks. And also, we'll try to use a liquefaction data set and enable liquefaction for this analysis. Let me show the documentation for this too. Or user guides. Water facility damage. So this shows that there is a parameter that says use liquefaction or not. And we can provide a liquefaction geology data set, which shows the soil parameters that is used for calculating the liquefaction. And you have to also provide a liquefaction fragility key. So it uses a set of liquefaction fragilities that we have in our database to calculate the liquefaction values. So this is a liquefaction dataset ID that we will use. So if I search for this in our data viewer, I can see that it is part of this Memphis liquefaction dataset, and I can preview it. And this is where it is. And you can actually download the dataset and load the shape files behind it on into your local QGIS or some kind of tool that you have on your local. So if I see, it looks like this, and okay. So each of these areas are represented by one of these attributes. It will show like what is the liquefaction susceptibility, what is the soil type being used, and all these other parameters that we'll use to calculate the liquefaction. And to start with the analysis, we'll first start with visualizing the water facilities dataset. So these are the input fields. So this has different facility types. So PPPL is for large pumping plant, PSTS is above ground steel tank, and there are 15 of the pumping plants and 34 steel tanks. So they are distributed across Memphis area, and similar to the other analysis, we'll import the water facility damage class and initialize it. I'll just see what I see some messages in chat. Okay, I'll get back to it at the end of the session. Okay, we are loading the remote input dataset, calling it water facilities. Again, you can get all these keys from the from our manual to see what fields are applicable and what the name of these keys are. We are setting the hazard type to be earthquake. Hazard ID will be the hazard ID. We are enabling liquefaction as true, and the liquefaction geology dataset ID is provided from what we set here. And we set all the parameters, similarly loading the mapping ID. Yeah, this is interesting because this mapping has both fragility. It has fragilities for both PGA and PGD. The PGD ones are used for liquefaction. So this is the mapping. So this shows that, so for PGA, if the backup power is 0 and the utility type is PDFLT, use this fragility key for PGA and this fragility key for PGD. So similarly for each of the different types. So for PSTAS, this is the fragility we are using. So I can again search for this and go to this tab and see how these curves look like for PGA. For limit state 0, this is the graph, and so these are the graphs for limit state 1, 2, and 3. So we initialize the mapping set, and then we set the parameter to PGA. We set the number of CPUs. This will be the output file. and we run the analysis. Okay, maybe I didn't run. Okay, I didn't run this cell. Sorry. Okay. So if I go here, you'll see again 2 more files. And if we are visualizing the output, similar to the other analysis, it will show all the different limit states, if it's exposed to hazard or not. And similar way, we can visualize it on the map for a damage state 4, which is for complete damage. Yeah, so this is a color code being used. There are some light yellow dots, some green dots, and some dark blue dots, where dark blue means less probability of being in damage state 4, and yellow dots means there's high probability of complete damage for these units. The output of this, I just want to quickly show, if we have time, the output of this, because we are using liquefaction, it will show more fields than what we have seen for the other damage analysis for tsunami. It shows the damage type used is PGA, the damage unit is G, the hazard value for the damage for PGA is 0.44 G. And similarly, for the liquefaction, this is the fragility that was used to calculate the liquefaction values. It says we use PGD and the unit is inches, and the liquefaction value is 99, and the probability of liquefaction at that point is 0.2. So if we don't use liquefaction, it won't show all these fields in the JSON file. And similarly, CSV is the same as similar to the other analysis. Okay. Yeah, that concludes the water facility damage, and next one is water pipeline damage with repairs. So this shows the buried pipeline damage. This is a buried pipeline damage analysis with earthquake, and the process for computing is pretty similar. It will also, in the output, we'll also see what the repair rate is, break rate is. The output of this analysis is slightly different to the limit state and damage state outputs that we have seen in the previous analysis. So we are showing the water pipe, we are initializing the data set and putting it into the data frame similar to what we have done for the other analysis. And if we see, this has all these different pipelines, a pipe type, a joint type, what's the capacity of each of these pipelines, what's the diameter. It looks like most of them have a diameter of 2 inches. What's the length of them? And the pipeline source, I don't know, maybe. Okay, so if we see them on a map, this is how all these pipelines are connected. And in this next part, we will configure the analysis to run it. We are initializing the pipeline damage object with the pipeline damage and damage repair rate class. And we're initializing the pipeline data set. Hazard type is same. We are initializing the liquefaction object here. Use liquefaction is true. And the mapping set is this. And then we can run the analysis. Okay. This should again create 2 more files with this name, pipeline damage with repair rate. So if we visualize the output of this, you'll see that we'll see that there are different columns compared to other analysis. It shows the PGV repairs, what are the PGD repairs, and how many repairs are needed per kilometer of pipe, and what's the break rate, leak rate, the failure probability, number of PGV repairs and number of PGD repairs, and the total number of repairs, which should be the sum of these two, and the hazard exposure column. This output can be used in other analysis as an input, for example, to calculate recovery times and other things. So similar way, we can use a plot join map method to visualize it on a map. So this is we are visualizing because we don't have limit states here, we are visualizing the number of repairs per kilometer. So the ones that are lighter in color means they are nearly like around 9 or 8 repairs per kilometer on these pipes. And the ones that are darker is where, like dark blue is where there are lesser number of repairs per kilometer.